How's it going? Hope you all are doing well today. Yeah, it's a little cold. Alright, does anyone have any questions regarding what we talked about last time or the other course or anything like that? Okay. Alright. Well, today we'll look at section 1.3, which is on factoring. And when we're looking at factoring, we're looking at polynomials specifically, which we discussed last time, just defining polynomials and basic operations. Factoring is the sort of division, but not exactly. It's more of a reversing the process of multiplication, because we talked about foiling expressions last time and multiplying expressions together. Now we want to take them apart again. Okay. So the first thing that we look at will be factoring a greatest common factor. Which sometimes we'll refer to as GCF, but usually we don't have to write it down anyway. And the idea here is we want to find the largest number and the variable with the highest exponent that is in common in all of the terms in the expression. Okay. So for example, if we have the expression 6x cubed minus 12x squared, what would the greatest common factor be between those two terms? So we have two terms here. Terms will always be separated by pluses or minuses. So what number, or what is the largest number that they have in common as far as a factor? And then what variable do they have in common? X. Can we do better than X? What about the numbers? We have a 6 and a 12. Is 6 a factor of 12? Six is a factor of 12, yes. One thing we don't want to mix this up with is least common multiple. Greatest common factor or least common multiple. I find students mix these up occasionally. For these two numbers, 6 is the greatest common factor. This is the largest number that goes into both numbers. 6 goes into 6 one time, and 6 goes into 12 twice. The least common multiple, or lowest common multiple, would be 12 in this case, because both numbers are factors of 12. But we want to make sure we're choosing the right one between 6 and 12, basically. Doesn't necessarily have to be these numbers, because in this case it happened to be what I chose. Okay. So we can 6 is a factor of both of these numbers, and that's the largest one we can pick because we can't go any bigger than this one. Now we have x cubed and we have x squared as our variable expressions, so they each have x, but more to the point, they both have at least x to the second power. Okay? At least x to the second, if not x to the third. So step one is identifying what the common factor is. Okay? So the biggest number that we can take out of a 6 is 6 itself. Okay? And it also happens to be a factor of 12. Oh, excuse me. Happens to be a factor of 12 also, so 6 works as our greatest common factor. For the x's, we take basically the lowest exponent that is in common with all the terms. So each of these terms have at least x to the second power. This one has to the third, of course, but they both have at least 2. So that would be our result there. Okay, so the issue then is, now that we've decided what the greatest common factor is, how do we actually factor it from these two terms? So we factor the GCF out. by dividing each of the terms by the GCF. Okay. And we also write the greatest common factor on the outside. So we have 6x cubed minus 12x squared. Now we know that we're going to factor out the common factor of 6x squared here. And what we do is we'll take each of these terms and now divide them by 6x squared inside. Okay. So what is 6x cubed divided by 6x squared? We know the 6's will cancel. 6 divided by 6 is 1. And then x to the third divided by x squared. The way that, and I don't know that we talked about this, the way that we divide exponents, terms with exponents, as long as they have the same base, the way that we divide these is by subtracting the exponents. So 3 minus 2 is x to the first. So it's really 1x to the first that we get when we divide those two together. What about 12x squared divided by 6x squared? It's a 3. 12 divided by 2. What power would that x have, though? It's not just x, it's a specific power. 0. Good. Yeah, remember we said if we have x to the m divided by x to the n, that's x to the m minus n. Okay. And so we achieve that by subtracting the exponents. 3 minus 2 gave us x to the first. 2 minus 2 gives us x to the 0. Now that leads us to a second rule that we need to introduce, which is that x to the 0 power is 1. In fact, anything to the 0 power is equal to 1. So, the way we rewrite this now is 6x squared and then x minus 2. Okay. In fact, when we see x squared divided by x squared, we could make that x the 0, or we can say, well, anything divided by itself is equal to 1. So x squared divided by x squared is just 1. 12 over 6 is just 2. So really, these cancel out, and then we just reduce these down to a 2. Same thing with 6 divided by 6. We don't really have to write the 1 if it's in front of a variable, like we did in this case. So we know 6 divided by 6 is 1, or we can just say it cancels. And so we have, okay, x cubed over x squared is x to the first. When we're first learning, though, it actually, I think, helps breaking it down to this point before we write it how we would actually want to express it, which is x minus 2. This middle step, I think, is kind of useful when we're first learning this. So, notice that if we were to distribute the 6x squared, 6x squared times x, now going backwards to here, we know that we add the exponents. So if this is x to the first, 6x squared times x is 6x to the third. And 6x squared times 2, it would be 12x squared. So really what we're doing is reversing the process of multiplication that we saw in the last section. So factoring, in a way, is division, although we don't really call it division. Okay. Let's look at another example. Sorry. Here we have 10y to the third minus 8y to the fourth. What factor divides evenly into both 10 and 8? A 2? Good. And 2 is the largest such number. There is no number larger than 2 that is a factor of both 10 and 8. And as far as y cubed and y to the fourth go, which of those will we choose to be part of our greatest common factor? Y to the third. Well, how we decide that, once again, is basically both of these terms have at least y cubed, so we'll use y cubed as our part of our common factor. Usually we pick the lowest exponent that's part of all the terms. Okay. Now again, we want to create our factorization, so we're going to take our 2y cubed and divide both of the terms by 2y cubed. Okay. So what would you say 10y to the third is divided by 2y to the third? Five y to the 0. Mm-hmm. Good. Good. And then how about the other one? 8y to the fourth divided by 2y to the third. Four y to the 1. Good. All right. And 5y to the 0 minus 4y to the 1. What would be a simpler way of writing that now that we've gotten that taken care of? Five minus 4y. Well, we would either write y to the 0, or we would just, since they are the identical, y cubed over y cubed, either y to the 0 or not anything at all. We would just write a 5 down there. Because y to the 0 is actually equal to 1, not y. So the exponent is important. Now y to the first power, that's the same thing as just plain y, because when we have y by itself, the 1 is implied there, and that's what's happening here. This is saying we actually have 0 y's, so it's just a plain 5. Okay. Now, if, again, we were to remultiply here, 2y cubed times 5, that would give us 10y to the cube. 2y cubed minus times 4y, that would give us 2 times 4 is 8, and then y cubed times y is y to the fourth. So the idea is if we multiply these back together, we should get the original term. And that's a good way for us to check our work. Especially if we're not confident in the answer, we could always remultiply and verify that it comes out to equal the same thing we started with. Okay, this time we're looking at 3 terms. We have 16x squared minus 8x plus 12. Now, when we look at our greatest common factor, now we're looking at 3 terms, again, the term that we choose for the greatest common factor has to be part of all 3 of these terms. Since the 12 does not have any x's, could we say that x is not going to be part of the greatest common factor? You got it, Luke. Good. Yeah, we could say that x won't be part of the greatest common factor. I didn't phrase that greatly, but yeah. But you're correct, Luke. The common factor here is 4, and that's it, really. We can't use x because x is not part of all three terms. The only thing we look at are the three numbers, 16, 8, and 12, of which all three of those, 4 is a common factor of. Okay? So this one's a little bit easier with just a number. So we know 4 is our common factor, and we're going to take each of these terms and divide them by 4. And so what is that going to give us? One. If we take 16 divided by 4, so it'll be 4x to the second minus 2x and plus 3. Good. And that's all we needed to do. The variables actually all stay the same in this case because we don't have any variables that are part of the common factor. There are no x's in common, so we won't have any x's over here. Because we're not dividing out any x's, we're just dividing a number 4, then we just divide the coefficients, 16 divided by 4, and leave the variable the same. 8 divided by 4, leave the variable the same. 12 divided by 4, that's our answer. Okay? And then we don't have to worry about simplifying that because all of our exponents are as we would normally write them. So it is a little bit easier in most cases just to factor out a number. Let's see. What about in this case? We have 10x to the third minus 25x squared plus 15x. 5x. It is 5x. Good. 5, of course, because we are looking at the 10, the 25, and the 15. All of them have a 5 in common. And nothing higher than 5, because we look at the numbers and we see nothing else makes sense. And everything has at least x to the first, or just plain x. We have x to the third, x squared, x to the first, so everything has at least x to the first. We wrote that as such over here. Okay. And so we're going to want to divide each of these by 5x. And again, remember that is 5x to the first. So 10x to the third over 5x, what is that going to give us? Two x to the 2. Yeah, 10 over 5. 10 divided by 5 we know is 2. X to the third over x to the first, we know we subtract 3 minus 1. That leaves x squared. How about the second term? Five x. Good. So we know 25 divided by 5 will leave us with a 5, and then x to the second over x to the first, we subtract 2 minus 1, leaves us x to the first, or plain x. Now if you wanted to make an intermediate step and write that as 5x to the 1, and then later change it to 5x, that's fine. But we know ultimately it will be 5x. And for the last part, three x to the 0, or just 3. Yeah, because both of them have x to the first power, we know 15x to the first over 5x to the first. 15 divided by 5, we already have that as 3. X to the 1 over x to the 1, we subtract 1 minus 1, so it's x to the 0, which again, x to the 0 we said is equal to 1. Which, I wrote that and then you can't see it. There you go. Now, we don't really need to write 3 times 1, because anything times 1 is equal to the original number. So we just write 3 there. If we can get to where we go directly from here to here and here to here, that is a goal. If you feel the need to go through this step, it's also important at this point that you go ahead and write that down, so you can make sure when you look back at your notes or you look back at this video, I've written it down here so that we see exactly where this 3 comes from. Excuse me. Okay. So that is factoring with the greatest common factor. I should call it, excuse me, factoring quadratic equations. Well, they're not really equations. You know what? Let me just start over there. Sorry about that. Factoring quadratic expressions, that's a better way of saying this. Now the reason we call them, we don't want to call them equations. Equations means that there's an equal sign present and that we're trying to solve something. By calling it a quadratic expression, that means there's no equal sign. It's just a string of terms added or subtracted together, which is what we've been working with so far. And this is a better way of describing what it is that we're going to be looking at. Now, I'm going to start off with a equals 1 as our scenario. Now what that means is that if we look at our quadratic equation, or a quadratic expression, I'm doing it again, but sorry about that. The general form for a quadratic expression is ax squared plus bx plus c. The idea is that we know that we're going to have x squared and x and a constant for every time we have a quadratic. But the coefficients are called a, b, and c. Those will represent numbers. We just don't know what those numbers are quite yet. And the idea is that we let a, b, and c be placeholders so that we can replace them with numbers when we look at an actual quadratic expression, rather than just this general case here. Now, we said a was equal to 1, so that means we're going to be looking at x squared plus bx plus c. And this tends to be the easier case, so we like to look at it first. Now the idea here of factoring a quadratic expression is we're reversing the process of FOIL. You'll recall that we discussed FOIL last time. This is a colon, sorry about that. Yep. So last time we saw x plus 2 times x minus 5, that's equal to x squared. X times x is x squared. X times 5, or x times minus 5 is minus 5x. 2 times x is plus 2x. And 2 times minus 5 2 times minus 5 is minus 10. And that gave us an expression x squared, and we combine minus 5x plus 2x is minus 3x, and minus 10. So the idea is we want to take this and factor to get what we started again, or with again. Okay? So how can we take this expression, x squared minus 3x minus 10, and figure out that it's equal to x plus 2 times x minus 5? So that's really the goal that we're trying to do here. Okay, so it's taking that same process of FOIL that we used to go from here to here, and now we want to go the opposite direction, from here back to the original pair of factors. So as you can imagine, it's a little bit more I would call it a little bit more difficult than the GCF, the greatest common function or factor. Now I'm starting with a equals 1, where we just have a plain x squared. This is the easier case of the two. We'll also look at problems where the coefficient of x squared is not 1, just to contrast that and see how we would handle those as well. But we want to focus on this first and get this down. Okay. So this is our, given x squared plus bx plus c. Here's our general approach. We want to find two numbers that, 1, multiply to c, and 2, add up to b. Okay? And I'll make sure I write that down each time. That way we can see what exactly we're looking at and what exactly we're trying to do. Okay? So example. And we're just going to start off with everything positive. That way we don't have to work in pluses and minuses at the same time, or just minuses to begin with. So let's try x squared plus 9x plus 20. Okay? So the idea here is we want to find two numbers that multiply to c. This time our c value is 20. So we want two numbers that multiply to 20 and add to 9, because b is our 9 in this case. Can you think of two numbers that fit that description, that they multiply to 20 and add up to 9? Four and 5? Mm-hmm. Good. And we always want to start with the multiplication, because we know a lot of things add up to 9, but only certain things multiply to 20. So 20 is where we want to begin with this. And we think about what multiplies to give us 20. Well, we know it's 1 times 20. We know it's 1 times 20. We know it's 2 times 10. And we know it's 4 times 5. There's multiple ways that we can get things to multiply to 20. However, only one of those combinations will also meet the second requirement that the numbers must add up to 9. And then we can identify, hey, that's 4 and 5, that not only do they multiply to 20, but they add up to equal 9. Okay? So that's why I write multiply, what number they multiply to first, because that's really what we want to start with. Think of the things that multiply up to 20, and then we figure out which of those combinations also add to the number 9. So the way that we create our factoring now is we do x plus 4 and x plus 5. That's our 4 and our 5 right there. And once again, if we want to check our work, we can FOIL these back together and verify that it does equal x squared plus 9x plus 20. Now some of you may already have experience factoring and you're comfortable with your approach, and that's fine. We're not saying that you have to do it any specific way. I'm offering you one way that should work for every expression of this type. Okay. So if you've looked at previous methods and they don't work for you, maybe this works for you. If you have another method that you prefer that already works for you, definitely use that. Okay. Hopefully we'll have at least something that works for us, and that's the goal. Okay. Let's look at another example. X squared plus 13x plus 36. So we want two numbers that multiply to 36 and add to 13. Four and 9. 4 times 9 is 36. 4 plus 9 is 13. So that's our combination. So x plus 4 and x plus 9. Does that make sense? Okay, what if we have x squared plus 7x plus 10? We need two numbers that multiply to this last term, 10, and add up to the middle term, 7. This and the GCF are two entirely different things, but I'll show you an example where we can use them together. That'll be one of the next examples. 2 and 5, good. So we have x plus 2, and we have x plus 5. Now, talking about the GCF, one thing that we noticed looking at these three examples that we can see on the screen, for each of these terms, there are no terms in common, or in each of these expressions, there are no terms in common. The numbers, since we have a 1, a 9, and a 20, there's no number that goes into all three of those. Technically 1 does, but we would never factor out a 1 because it doesn't really change anything if we divide everything by 1. So none of these numbers have anything in common that we could factor out. And in general, for a quadratic expression, the x's won't have anything in common either, because the last term is generally going to be a constant. So we won't ever have any x's there that we could take out from all three terms. So the first thing that we notice is that these three expressions that we just looked at, they don't have any greatest common factor. So there's nothing to factor out there. However, if there is a greatest common factor, we always want to factor that out first before we do anything else. Let me show you an example where that's relevant. For example, let's see. Let's do 3x to the 4th plus, and I'll just keep everything positive still, just to eliminate one additional step or element. Let's see. So this one will have to be bigger. Let's say 12x to the 3rd and 9x squared. That'll work. So first thing we have to figure out, now anytime we have a factoring problem, the first thing we check for is greatest common factor. Because if we can take out a common factor from this, that'll simplify the part that we still need to factor afterwards. That's a quadratic trinomial, or whatever it is we end up with. So what is our common factor in this case? Three. Definitely have a 3 in common with all these terms. What about for the variables? X squared. Yeah. So all of them have at least a 2, because we have 2, 3, and 4 as our exponents. So the 2 is the smallest of the 3. So we'll use x to the 2nd. Okay. So we need to take a 3x squared out of everything before we do anything else. So with 3x to the fourth divided by 3x squared, what is that going to leave us when we divide those? X to the 2, good, x squared. Yeah, 3 divided by 3 we know is 1, so there's really no need to write the 1 in front of that, as long as there's something else here. And then x to the 4 over x squared is x to the second, because we subtract 4 minus 2 is 2. Good. What about our middle term? For x. 12 divided by 3 gives us 4. We know that. And x to the third over x squared, we take 3 minus 2 gives us x to the first, x to the 1. Now again, we don't have to write the 1, we can just write it as a plain x, and that means the same thing as x to the first power. Lastly, 9x squared over 3x squared. Plane 3, good. Okay. So that means now we've successfully factored the common factor out, but now we still have a trinomial, a quadratic trinomial, that we can factor into two binomials. So we can factor this as well. And we'll say that we need two numbers that multiply to 3 and add to 4. So what two numbers would that be? Three and 1. Good. Okay. And so that would be our complete factorization of this original term. We took out the common factor first, and then we factored what remained into two parts. Depending on the expression, after we take out a common factor, we won't always be able to factor this. It just depends on what we have. But we always look to see if we could break this down any further, since it's quadratic. Again, x squared, something times x, and a constant. We know if it is factorable, it's going to follow this pattern that we need two numbers that multiply to equal this last number, 3, and also add up to this middle number, 4. Okay. So there's a lot more that goes into that because of the common factor, but it's really the same things that we were doing, just combined into a single problem. We do the common factor first, and then we look at whatever's left over and then factor that again. Okay, we'll do one more of these before we start introducing negative signs. What multiplies to 54 and adds to 15? This one's a little more challenging. I'll give you a hint. Both of the numbers are smaller than 10. 9 and 6. Good. I figured that's what you mentioned. Okay, yeah, 9 times 6 is 54, and 9 plus 6 gives us 15. It's a little more challenging because as we go with higher numbers, one, there's a lot more ways to factor that, and the ways are more complicated, and two, not as many people are as familiar with those factorizations the higher we go versus the lower numbers. We'll generally stay within our multiple products all the way up to 12 times 12 because that's what we generally learn and are comfortable with. So I'll try to keep it within that, but yeah, this is nines and eights in particular. I know give a lot of people trouble, so that's why I like to include those. All right. Let me write down the factorization, of course. So x plus 9 and x plus 6. Okay. So what happens then if we make this number a negative? So let's say x squared minus 11x plus 30. Well, the same principle still applies. It has to multiply to 30, but this time it has to add up to negative 11. Now, let's think about what that means before we figure out what the numbers are. If it multiplies to a positive number and adds up to a negative number, the only way that's possible is if we multiply a negative times a negative, that gives us a positive, and if we add a negative and a negative, that equals a negative. So what that tells us is now both of these answers are probably going to be negative. Okay. So what two negative numbers can we multiply to give us 30 and add up to negative 11? Yes, negative 6 and negative 5. Multiplying, these give us a product of 30, and adding, they add up to a negative 11. So the fact that this was negative means that they still multiply to a positive number but then add up to a negative number. The only way that's true is if both numbers are negative themselves. So we know a negative times a negative is positive, and a negative plus a negative is negative. So now we have to have a little bit better understanding of how combining numbers works and making sure we're okay with that. Now when we write our factorization, we'll just include negatives instead of positives. So it'll be x minus 6 and x minus 5. Okay. Any questions there? Certainly we're going to do more of these, but I just want to see if everyone's okay with that one before we move forward. Okay. So let's do x squared minus 11x plus 18. So we want two numbers that multiply to 18 and add to minus 11. -2 and -9. Good. Okay. So these examples are really not that different from where we had a positive there versus a negative. The only difference is both of them are negative instead of both being positive. Okay. So x squared minus 13x plus 40. So we need two numbers to multiply to 40 and also add up to a -13. So we think about what multiplies to give us 40 in the first place. There's not too many different combinations, but only one of those combinations gives us 13, or -13 actually, which is -5 and -8. Good. Okay. Sorry. There we go. So that's another strategy we can use, is we can write down, what we're multiplying to, and then write out the factors. And hopefully we land on the one that we need. If it happens that we forget the factor that we need, then we might be in trouble. But we can also, you might recognize, just looking at 40, we know 5 has to be a factor. So if you're not sure what the other one is, we can just take 40 divided by 5, and that gives us the 8. Alright, now let's change it up a bit again. This time, instead of this number being negative, I'm changing it to the other number's negative. The last number's negative. So we want two numbers that multiply to negative 18 and add to a positive 3. Now what we'll see is true here. If we have two numbers that multiply to give us a negative, one is positive and one is negative. That's the only way that is true. So it has to be a positive times a negative to equal a negative. So the two numbers we're looking for, one's positive and one's negative. Now they add up to a positive 3, so that also tells us which one should be which. 6 and negative 3, good. And again, we can verify this. 6 times negative 3 is negative 18. Positive 6 plus negative 3 is positive 3. This tends to be the hardest of the three types where we have our minus sign. So if the last term is minus, then that means we have mixed signs. And so we know that not only do we need to figure out which combination of numbers works, but we have to get the signs in the right order also. Because whether we say 6 and negative 3 or we say negative 6 and positive 3, it makes a big difference because they may both multiply to negative 18, but only one combination adds up to a positive 3. Okay. This time we have two negatives, which is kind of in the same category. Multiply this to a negative 35 and add to a negative 2. It's really the same concept as we just looked at, except the numbers have to add up to a negative number instead of a positive. Negative 7 and 5. Those multiply to give us negative 35, and negative 7 plus 5 is negative 2. Now, one way that we can figure out which one's positive and which one's negative, if they add up to a positive number, that means the bigger number must be positive for that to happen. And if they add up to a negative number, then the bigger number must be negative for that to happen. And so that's another way we could tell which way that's going to go. Let's see. Let's say x squared minus 5x minus 50. So we have two numbers that multiply to negative 50 and add to negative 5. Negative 10 and 5, good. Negative 10 times 5 is negative 50, and negative 10 plus 5 is negative 5. Is everyone understanding this okay? Here we're going to multiply and get negative 32 and add the numbers and get a positive 4. Mm-hmm. 8 and negative 4. Because our product is negative 32 and we have positive 8 minus 4 equals 4. Okay. Alright. So that really covers everything that we need to do with these with this case where we have a trinomial or quadratic trinomial and a is equal to 1. Now we need to look at the case where a is not 1. I think we're up to part C. And so the idea here is that we have ax squared plus bx plus c. And this time a is something besides 1. When we had it equal to 1, it made it a little bit easier overall. But when it's not equal to 1, it does make it more challenging. Okay. This time we're looking for what multiplies to a times c and adds to b. So it's actually pretty similar. Technically we can think of it as the same rule, but the process ends up being very different, because once we figure out these two numbers for which this is true, it's not the same as what we did here. We just say, right, okay, x plus that number and x minus the other number. It's a little bit different when we have a in front, and we'll go over how we do that. First thing, though, is to figure out exactly which two numbers make this true. Once we can establish that, then we can move forward. So it's slightly different. Rather than multiplying to c, we're multiplying to a times c, which technically we could say we were doing before, because, looking at this example up here, a is 1, c is negative 32, so 1 times negative 32 is negative 32. So technically we were doing the same thing before, but we didn't really worry about it because it's easier just to say whatever the c value is rather than a times c. Unfortunately, these are harder to make up problems on the fly, so I'm going to have to pick out some of the even ones from the text. And then we're absolutely having homework on this stuff. There's just no way around it. Anyway. This is 26 on page 24. What is that, a U? Or W? W, okay. 3w squared minus 8 times w plus 4. Okay. Notice they're using w here instead of x, but that doesn't really change anything. We just want to make sure we stay consistent with the variable that they give us. Okay. Now we look at a and c, which is 3 times 4. And that gives us 12. And we want the numbers to add up to negative 8. So what multiplies to 12 and adds to negative 8? Negative 6 and negative 2. Good. Negative 6 times negative 2 is positive 12. Negative 6 plus negative 2 is negative 8. Again, in this case, because it multiplies to a positive and adds to a negative, we need two negatives. Now, the way that we proceed here is different than what we had done before. So what we're going to do is we're going to take this minus 8w right here, and we're going to split it into two parts. We're going to split it to minus 6w and minus 2w. And we can see where that came from. That came from these two numbers. So instead of minus 8w, I'm going to make it negative 6w and negative 2w. Now, I don't believe we've talked about factoring by grouping, because that's another method that we have. But this is where we apply what's called factor by grouping. Now, factoring by grouping is a different process than what we've been doing. It's used when we have four terms, such as this one. Group the terms into two pairs using parentheses. Let me make sure I'm in the screen. Okay, so that means we have 3w squared minus 6w plus negative 2w plus 4. Now notice what I did here for this first step. We grouped the group terms into two pairs, so I put parentheses around the pairs. But what I did is I went ahead and put parentheses around both of these parts and just put a plus between them. Now, with this plus between them, remember, we're not actually multiplying these binomials. We're adding them, so we don't try to FOIL them or anything like that. We're just working with them as they are. Our second step of factoring by grouping is we factor the greatest common factor from each of these terms in parentheses, or from each set of parentheses, I guess we could say. Okay, so for 3w squared minus 6w, what's the GCF there? So negative for 3w squared minus 6w, what's our greatest common factor? For 3 and 6? 3 and 6 have what factor in common? 3. W squared and w to the first, they have a w in common. So it should be 3w to the first. Okay. Now minus 2w and 4. Now this time both numbers do not have w, so there is no w in the common factors, but negative 2 and 4 do have a number in common, and that would be 2. Good. So we want to take 3w out of this first set of parentheses. So 3w squared will be divided by 3w, and 6w divided by 3w. And we want to take a 2 out of the second set. Now the second set starts with a negative. Let's take out a negative 2 from everything. Okay. Generally, this will be what we need to do. Anytime this is positive and this is negative, we need to take out this negative. So basically, anytime we see a negative here, let's include that negative as part of that factor that we take out. Technically, negative is not part of the common factor, but because we start with a negative, let's factor that out. That's the reasoning that we're using there. So what is left in this first parentheses after we divide out the 3w? get a W minus 3. 6 divided by 3. Yeah, remember the constants we divide, the variables we subtract the exponents. Yeah. So that'll be W minus 2. Now what about on the second set of parentheses? What do we have left inside? W. And again, divide these. If we have 4 divided by negative 2, negative 2. Good. Okay. All right. Third step is we notice that and this should happen every single time, we have the same expression left inside both parentheses. Let me, I think I have room over here. So currently we have 3w times w minus 2 minus 2 times w minus 2. So step 3, we should have the same expression left over inside each set of parentheses. Okay. And because we have the same expression left over in each set of parentheses, we can factor that out. Now, this is a little bit strange because now we're factoring a binomial. So we can factor the binomial they have in common. So if we take a w minus 2 out from both of those terms, the question is, what do we have left over? We take the w minus 2 out here, we take w minus 2 out here, so that because it's part of both, we factor it out to a single factor. And then what's remaining for each of the other two parts? 3w minus 2. So what's left over here becomes the other binomial. Now, this problem is not as difficult as it currently seems because we went through the discussion of how to solve the second part as we solved it. We can see it's definitely more involved than what we were doing in the earlier parts, but it utilizes a lot of the same things that we've been talking about this section, which is the greatest common factor, because that came up again, and the original factoring that we did. Okay. So to recap, this particular problem is kind of a doozy. We had that A is 3, C is 4, so 3 times 4 gives us a 12. So we know we need two numbers that multiply to 12 and then add up to the middle number, -8. And we decided that was -6 and -2. -6 times -2 is 12. Adding them equals -8. So, when we figure out what those two numbers are, that's how we split up the 8w. This is in the middle, the -8w. We split it up in the -6w and -2w, like we see here. Now, from there we go into our factoring by grouping. So we put each of these in parentheses. We put the first two numbers in parentheses and the last two numbers in parentheses, and we put a plus sign between them. After that, we set up our two groups. We factor the GCF from each group. So for this first set of parentheses, the common factor is 3w, as we found here. And for the term in the second set of parentheses, the common factor is 2. So we took 3w out of the first group. Now we went ahead and did a -2 for the second group because we had this minus here. Anytime this term starts with a minus, let's go ahead and factor out the negative. That's the other thing I should have written down. But anytime we have a minus here, let's go ahead and factor that out. So we factor out a -2 instead of just a 2. The reason we want to take out a negative specifically is to end up with this being a positive w, because we want these two things to match. If these two things don't match, we can't continue. Okay? So we got this expression left over. Now, I rewrote it over here, and we said from this point, we should have the same expression left over in both sets of parentheses, which we do. And then we can factor this common binomial, w minus 2, because both parts of this expression have w minus 2 now. Our groups have to refactor them. So that w minus 2, it gets factored out here, and then whatever is left over, 3w and minus to 2, get put together, and that's our other factor. Okay. Let's do one more of these before we go, just to see how we're doing with this. This will be problem 28. It gives 8x squared minus 14x plus 3. Now we're going to need two numbers to add to -14, but in this case, what are we going to need the numbers to multiply to? Now remember, we multiply the first and the last number, 8 times 3. So we're going to need the two numbers that we get to multiply to 24. So two numbers that multiply to 24 and add up to negative 14. Again, with a positive product and a negative sum, that means the numbers should be both negative. So what two numbers work for this combination? Negative 2 and negative 12. They multiply to give us positive 24 and add up to negative 14. Okay. Because we're working with a number in front of the x squared term like we are here, this time, instead of factoring, we're going to split up the negative 14x in the middle. Negative 14x is going to be split into two terms, minus 2x and minus 12x. Now, one thing you may be wondering right at this moment is how do we know to put the minus 2x first and the minus 12x second? Turns out we don't. If we switch those, we put minus 12x first and minus 2x second, we should end up with the same solution at the end. Okay. The paths will be slightly different, but the destination will be the same. Okay, now we split these into groups. 8x squared minus 2x, negative 12x plus 3. And again, we think about what is the common factor for each of these pairs. In this first term, what is the GCF? Well, between 8 and 2, 2 goes into both numbers, and each of them have at least x to the first, so 2x is our common factor. And we repeat that for the second term here, GCF. Now, again, because we start off with a negative sign here, I'm going to go ahead and include a negative as far as what we end up canceling out. And you think about, okay, they don't have x in common because this one doesn't have any x's. But we look at the 3 and the negative 12, and we see that both of them have a 3 in common. Both of them are divisible by 3. Okay, so we're going to take a 2x out of this first term, and a negative 3 out of this second term. Eight x squared divided by 2x, we know 8 over 2 is 4, and x to the second over x to the first, 2 minus 1, is x to the first, or just 4x. 2x divided by 2x, 2 divided by 2 is 1, and x to the first over x to the first is x to the 0, so we just get a 1 there, and probably a better way of saying that is because these are identical, we know it's just going to be 1, because anything divided by itself is equal to 1. And we have our minus 3, and then negative 12x divided by negative 3, we know the negative 12 over negative 3 is a positive 4, and the x, because there aren't dividing by any x's, the variable stays the same. So you get 4x. 3 divided by negative 3 is negative 1. Okay. And now we have the 4x minus 1 in common, so we'll factor that out. And we look at what goes with that now as our other factor. Well, that's our 2x minus 3. Okay. Basically, the common factors that we factored out, we put those together as the other factor. And that's the easiest way of expressing that. Okay, so 4x minus 1 times 2x minus 3, that is the proper factorization of our trinomial. As far as homework goes, on page 23 in the book, I'm going to have you do one, 3, 5, 11 through 24, and then 25 and 27 I would like you to practice. Now, you can work those just from the book and turn in your work. I'm going to try to get it set up as something from my math lab. Again, that requires some communication that has to happen, so hopefully it'll be successful this time. But I definitely want you to practice these because they do take some work, and I know that we need to work on these based on the responses I was seeing. So hopefully we made good progress today. But this is a complicated topic, and it's useful for what we do. Coming up in the other course, I think it will be an issue. So definitely need to work on this. So I encourage you to look at these problems. But yeah, I'll work to get them set up in my math lab for the other course so that y'all can work on it there. Okay. Probably just by next Monday. Yeah, just have a week to do them. We're going to continue in this same section on Wednesday, so I might add to that. But just for now, I would say go ahead and work on these if you want to go ahead and get started. Okay? Let's see, so due October 26th, Monday. Just by class time, you don't have to turn in by midnight or something like that. Alright, well, y'all have a good rest of your day. Look this stuff over, and I'll see you again on Wednesday. Take care.